Just want to check
Like that system is like takes care of it.
should be good. People on Zoom can hear.
Yeah, I think so.
Okay, good.
Yeah, so welcome to the Theorem seminar. It's my pleasure to introduce Surachai intern Tawanchai. He's done some great work on graph algorithms, and then he's going to tell us about vertex connectivity.
Thank you for the introduction. So this is joint work with Takakon, and I'm going to tell you more about how to solve vertex connectivity deterministically in almost linear time for small connectivity. So let's get started. So let me first define the problem. So given a graph G, undirected graph with n vertices and m edges, we want to compute the minimum number of vertices such that we disconnect the graph. So in this particular example, the minimum vertex cut is 2. And then because you cannot remove only one node, but you can remove 2. Okay. And I'm gonna tell you briefly the history of the problem, what are the state of the art. So I want to tell you a bit more about on the sibling problem first, which is edge connectivity. So the problem is similar to vertex connectivity, except that we remove the edges instead. And for the edge connectivity, it's much more well studied. And in '93, Cargos have a beautiful random contraction-based algorithm that gives you n squared running time. And the first near linear time algorithm is also due to Cargo in 2000, and it takes about 20 years later to have a deterministic algorithm that is in almost linear time. It's very recent by Jason. And what do we know about vertex connectivity? So for sparse graph, and Kaufman showed that we can do something like n squared time, and then O sub c means I fix c to be small. And slightly better, and then the state of the art were due to Hasinger, Rao, and Gable in '96, which running time was MN, and it's randomized. And very recently, there are a lot of development in vertex connectivity, and now we know how to do in polylog macro. And due to the also macro being linear now, so we also know it also automatically implies that we know how to do vertex connectivity in almost linear time, which is randomized. And what do we know of? So here's the situation. In the edge connectivity, the complexity is known, like we know completely for deterministic, then that is almost linear now. And what about vertex connectivity? What about the state of the art? Not so much, but it's, in fact, the bound m times n is still open for vertex connectivity deterministically to match the bound. And the state of the art is due to Gable with a slightly more complicated running time, but the upshot is like it's almost mn. It's really close to mn now. And C here is connectivity. Okay. And the linear time algorithm are known for very fixed small connectivity up to 3 by Python BFS kind of algorithm. And the result that we have here today is that we give the deterministic algorithm of this runtime of this form. It's almost linear and it has dependence 2 to the c squared. And it's in particular, it's almost linear for whenever c is constant. For any constant c, it is almost linear. Right? And this is also the first improvement since 1969, even on sparse graph and on spatial case. So this is the new result. And for the next, I'm gonna tell you all the key techniques at a high level. So I won't give you a lot of detail. The first tool is called we look at vertex connectivity in expander. So we know that we show the first is that in expander it's easy to solve vertex connectivity, and the new tools that we introduced, there are two. One is that we show the reduction framework to vertex expander and something called T-splitting cut, or it's also known as the Steiner cut. And the second tool is that we introduce a fast vertex sparsification that preserves the connectivity, which is independent of interest. So it can be also useful outside of this context, I believe. So let's continue. Before I explain detail, let me just set the location stress that I'm going to use throughout the talk. So S is a vertex cut or simply a cut if G minus H means like I delete the vertices and then the remaining graph is disconnected. And the vertex cut you can also we can also view as a partition form that we have separator S and then you separate some component L and component R, where L and R have no edge between them. So this is also the vertex cut in the partition form. I say that the cut is T-splitting, meaning that I give you a terminal set T. Splitting means that the T has to be somewhere in L and in R. This is like split the terminal T, so this is called T-splitting. So next, I'm going to tell you that in expander is easy. I just want to define a few things about expander. So given vertex cut, which is L, S, and R, we can assume without loss of generality that L is smaller than R and in a directed graph. And the expansion is defined as the following, that the ratio of S over L plus S. So this measure literally the fraction of S that is inside on the cut. And so for example, if you look at the end node path graph, the following cut has very low expansion. So if you cut in the middle, then you get into quite balanced cut. So low expansion is also known as the cut is sparse. It's also another name. And another example is that if you cut this way, this cut has high expansion. For example, if L and S are kind of very close to each other, this is a high expansion cut. And one way to define expander is that it's a graph where every cut has high expansion. So there's no low expansion cut. So this is called expander. And the key property of expander in this context is that if you fix the cut S to be very, very small, and then the graph is have high expansion, it's implied that the L side has to be small. But we're gonna assume the following fact that it is known from the previous work that we can solve vertex connectivity in expander in only like linear time. So this is the fact that using the local algorithm, you can solve this. And we're gonna assume this fact throughout the talk, and that's the fact that is known in the prior work. And now we're gonna I'm gonna tell you how to handle general case. So in general, the graph is not an expander, and then I'm gonna tell you how to do it. So if the graph is on expander, well, we can find a low expansion cut. Let's say it's L, S, and R, and we get a to low expansion cut. We can define the following graph. It's called G sub L and G sub R. So I define the following. Given the low expansion cut L, S, and R, I define G sub L to be the graph G after replacing the right component R with a clique. of size C in here. And then I add bi-clique between S and the clique. So this is G sub L. And then I define the G sub R kind of the same way, symmetrically on the other side. And the key property of this is that it allows us to recurse on this small graph to find the cut. So the key lemma is that given the separation, given the vertex cut, here, this graph GL and GR are completely characterize the connectivity of G. It means that G is C connected if and if every cut that split S and T inside S is at least C, and GL and GR are C connected. So this is the key lemma, and I will sketch a bit how it works. So let's consider the following lemma in this form, that if G has a cut, then the cut either split the set S, meaning that the cut split S somehow, or if it does not split S, then that cut has to cut some smaller G sub L or G sub R. Okay, and so let's consider if G has a cut S prime, if the separator S prime split S in this way, then we are done. So we have the first condition, right? And what happens if S prime does not split S? It also means that with some work we can show that S prime that has to be inside L union S. So it won't be inside R. And if this is true, it means that by doing this contracted operation on G sub L, then we can show that S prime here is actually a cut in G sub L. So this is roughly the proof will go something like this. And any questions before? If you can stop me anytime if you have questions. Okay, good. So given this lemma, like I give you a separator, the vertex cut L, S, and R, then I can characterize this by constructing G sub L and G sub R, right? It means that it immediately gives us a recursive algorithm, right? That so the recursion is like this. Suppose I want to find a cut of size C inside this graph. So first I check whether the graph is expander. If the graph is an expander, then we are done. We can just use the previous work and solve the vertex cutting expander. If the graph is not an expander, then we find the sparse cut L, S, and R, and we apply and then we're gonna apply the previous lemma, right? So the algorithm is this, that we also check whether or not there's a cut that split S here. If there's a cut that split S, then we are done. We also obtain the cut. And otherwise, I'm gonna recurse on this G sub L and G sub R and so on. So this structural lemma immediately give us this recursive algorithm, and the correctness kind of follow from this lemma. Yeah. At least is the correctness of this algorithm more or less clear.
So when you say ST main cut, it's the edge main cut. What is it the word?
Sorry, yeah, this ST main cut means the vertex main cut. Yeah, sorry, yes. So when I say main cut here, when I say cut here, it's always vertex cut. Yes. And then right. So for example, in this left figure here, S prime here is XY mean cut, for example. So yeah, it always means vertex cut. Any other questions? Yeah.
Is the case where S prime, where it's like split, where is that happen?
So if S prime split, it means that ST min cut has to be smaller than C.
Oh, okay.
Yeah. And then if we can find at this stage, then we are done. Yeah. But if there is if the cut does not split at all, then we're gonna repeat at this end return. Yeah, so that's the recursion. Okay. Good. And so we have this recursion, and one thing that is very interesting is that given this lemma and this algorithm, we can kind of unroll the algorithm until we finish, until we obtain the best case. and we can state the lemma in a non-recursive form by just unrolling this algorithm. So then what would be the statement of this? So let's see. So let's consider the recursion tree of the previous algorithm. Now, this figure, let me explain slowly. So I'll start with G. And then if the graph is expander, we are done. If it's not expander, we will find a sparse cut. Let's say this is S. Okay, at this level, I find G and then the sparse cut S. And then I recurse on G sub L and G sub R. Right? And on G sub L, if it's an expander, then we are done in some sense. Otherwise, we find another sparse cut and recurse. So this recursion tree consists of the leaf nodes which correspond to expander, and then the internal node correspond to sparse cut. Okay, so each internal node we get some sparse cut overall.
Are you testing whether it's an expander, approximately an expander at every step?
Yeah, so we use a cut matching game to find the sparse cut. Yes, that's a great question. Yeah, it's not trivial. Yeah, to find a sparse cut, then we need the cut matching game. Yeah. Now let me state the unrolled version of the recursion lemma. So I define capital T to be a terminal set, which is the union of all the sparse cuts that we found during this algorithm. So look at each of the internal node of this recursion. I take all the union in the terminal set. And I define the collection of expander, which is obtained by the leaf node in this recursion. So the framework says the following: given a graph G, then there's an algorithm that output a set of expander at the terminal. So in this figure, the red thing is expander and terminal is the blue thing. Just to be clear. And then the lemma is this: it outputs expander and terminal in such a way that if you find a cut in G, it either split T or it cut in expander. So that's the unrolled version of the statement. And now I'm ready to state the reduction theorem. So all the previous slides are to motivate this following reduction framework. So given a graph G, we can output the terminal T and a set expander such that the first property holds that we mentioned earlier. And furthermore, there are also some nice property that we can guarantee further, which is the second property is that the set of terminals is at most n over log n. It's not the entire graph, it's small enough. And the total nodes of the expander at the total combined is also roughly almost linear. And we can do this in almost linear time. Yes. But I'm not going to go into detail of this, but only one thing I want to give you an idea how can we expect this to happen, because the recursion can be quite long somehow if you do the recursion and so on. But the argument follows from this that we want to show that the recursion depth is small. So if the recursion depth is small, then we get this property. To make sure that we get the small recursion, we're gonna use we not only define the sparse cut, but we find the approximately balanced sparse cut. So if a graph is not expander, I find a sparse cut. Among those sparse cut, I find the one that is like the most balanced. And then the property of the most balanced sparse cut allow us to have the polylog recursion depth. And this is the standard argument in expander decomposition. But this is the only high-level idea I want to give you for this reduction theory. It is clear, then I will continue. So this concludes the first reduction theorem, and even we have this, then there's still one challenge left. So let me tell you the challenge. So consider that I want to find a cut of size C in the graph G. We apply the reduction framework. So in linear time, we output a set expander and terminal, okay? And it has some nice property that it's completely characterized the cut. The cut either split T or it cut expander. Also, the terminal that is output is guaranteed to be n over log n, not the entire graph. So the algorithm is just this, right? Run this framework, and then I'm gonna verify whether or not it's a cutting expander, and run the previous framework. If I can find one of the cut in the expander, then I'm done. But otherwise, by the guarantee in this property, in the first property, it says that if none of the expander has a cut, then the optimal cut must split the terminal T. The cut has to split the terminal. Now, one at least the challenging or the funny part is that find, so it can give us the problem called the minimum T splitting cut. So like this framework, we get the minimum T splitting cut, but it's kind of harder than the min cut, min vertex cut by itself, because you can set T to be the whole graph. But actually, we have some progress because the second guarantee that we have, the terminal is not the entire graph. So we actually manage to make some progress here. And our approach from this is that if I know that there's some cut that split the terminal, then I'm gonna somehow compress the graph that preserve this cut that split the terminal. So that's the approach, that I will compress the graph to be some smaller graph, and then it preserve all the splitting cut. And the goal is that if we can do this and then say that the smaller graph has size only half of the original graph, then we can kind of recurse on this graph, and then we repeat again only like log n time, and then we are done. Okay, so this leads to the final tool that we need here, which is the vertex Sparsifier that preserve the vertex min cut.
Is there a loss in doing that? Is there any approximation?
So the cut preserving is exact, but it's parameterized by only if you guarantee that it preserve cut only small cut. Yes. Okay, so this at least the motivation is clear for this tool, how it's going to be used later. And now let me define you this object. I name it TC Sparsifier. So T is a terminal set that I care about, and C is the parameter that of the cut parameter. So given a graph T and terminal T, I say that another graph H, which is not necessarily a subgraph, it can be any graph, is a TC Sparsifier if there are two properties. S is cut preserving, parameterized by C, meaning that some cut in G that split the terminal T is preserved. So this is cut preserving. And the second property is called cut recoverable. It means that in the smaller graph H, there is no new cut in the smaller graph H. So if we have there is no new cut in graph H, it means that the minimum cut of this graph has to be at least the minimum cut of the original graph. And at least a definition.
Is there a relationship between H and G? Is it a subgraph or a minor or
It
something?
doesn't have to be.
Just any graph?
Yeah, it can be minor or something like that. Okay, so this is also known in the literature. So let's see what do we know. So there is a Sparsifier of size T cube by the work by in 2012. And if you want the size of T policy, then you can check Liu as well. But both algorithms are randomized, and then it takes polynomial time to solve. And it's not fast enough for our purpose. And but for the edge version of this Sparsifier, there is also a fast algorithm by Parinya and many others. You can compute in almost linear time and get the Sparsifier of size T policy here for edge version. But for our purpose, we need a TC Sparsifier for the vertex version, and we want to do it deterministically, and also in almost linear time. And we can afford to have some slightly larger on the function of C a bit, but we want linear in T. Okay. And then the second the result is that we can compute such a thing. We can compute such a TC Sparsifier in almost linear time where the size of the sparsifier satisfies this property is T and then exponential in C. But the key property that I want to tell you here is that this size is independent of the original. It just depends on P and just a function of P and C. Okay. So from now, let's assume this sparsifier and see how it implies the fast algorithm for vertex connectivity, and then I will at least sketch you how to get this sparsifier. So here we have the tools already. We have a reduction framework expander and also have a sparsifier. Now let's see how can we combine them to get an algorithm. So then we do the same thing. So given a graph, I want to find a cut. So the first step is to run this expander and terminal reduction, and the algorithm will try to find C cut in every expander. Okay, look at this expander and find every cut, and then if you don't find any cut, then we're gonna proceed with sparsify this graph on this set of terminal, and then it has some nice property that this sparsifier is like it preserves some kind of split key, and also there's no new cut in this graph, and also the size of the sparsifier is function of T and C. So we have this, and then if we can do this, we repeat, and here's the whole algorithm: run expander terminal, try to solve each expander, then sparsify and recurse. And what would be the running time of this algorithm? So in the reduction framework, it takes like almost linear time in the first step, and then solving or expander takes roughly a linear time expander, but the reduction guarantee that the total size is also almost linear. Okay.
Do I think of the second step there as like contracting all of the expanders? Is that roughly what's happening? Something else.
Exactly. The second step.
Yes, Sparsify GT stuff.
It's more like contracting the non-terminal part. Yeah, that would be the right way, because the second step does not take an expander as an input. It will sparsify the terminal. Yeah.
Okay, thanks.
And then the sparsifier will run in linear time n times C. So the algorithm is super simple, but what would be the number iteration? So we know that T is n over log n given by the reduction framework, and we know that the sparsifier is something like T times 2 to this. Then we will get some bound of this form, that n over log n times 2 to the C. And let's assume for now C is small for our purpose. This is roughly like half, and then we repeat this log n iteration. So this is the algorithm. And how about the correctness? So let's list the property. So here I know that the reduction framework says that the cut either cut G. If there's a cut in G, then it either split T or it cut expander. Okay. And so the correctness, I want to show that if G is C connected, then S is C connected, and vice versa. So if we have this, then we're gonna recurse until the base case.
Okay. So when you say cut and expander, you mean like the S lies in that red part? Or
so it means that the expander, the vertex connectivity expander is smaller than C.
Yeah, but like, do I just look at that one red piece? I mean,
One red piece, exactly. Yeah.
throw away the rest of
This is a bunch of expander. Yeah. When I say cut expander, it means that one of the expander here there is some minimum cut that's smaller than C.
I throw away the rest of the graph. Just look at that red part.
Yes.
Yeah.
One red piece.
One red piece, one at a time. But we guarantee that the total size of the expander is not too much.
Sure.
So let's say if G has a cut, and then an expander has a cut as well, then we are done, because the algorithm says that we're gonna run with the algorithm says that we're gonna check cut in every expander. So now let's assume that the graph has a cut, and the expander is C connected. I cannot find any cut in the expander. Then it's guaranteed that there has to be a cut split T. What happened is that then it also means that graph H must have a cut because the Sparsifier says that I will preserve the cut at the split terminal. What about if this is connected? Then, well, if the characterization says that expander has to be C connected, and then we cannot find any cut split tree. This is the property that guaranteed by the reduction framework. And because the graph H is cut recoverable, meaning that it's a mean cut. If mean cut in S is at least mean cut in G. So and therefore H has to be C connected. And this completes the whole framework. And so I guess now the remaining part of the talk will be on at least the thesis Sparsifier. I'm gonna at least sketch the idea how to do it. And any question before I proceed?
Also, is there like,
Yeah.
I don't know, maybe you told us already, but in expander or a vertex expander,
Yeah,
is it easy to see why it's easy to find a C cut? Like, this one.
Yeah, I guess it's not obvious, but one key property of expander is that
So it'll be a small set.
yeah, you can find unbalanced cut. I mean, yeah, but we can use local algorithm that kind of can test whether if you give a starting point, then it will detect whether or not it's part of the smaller cut or not. This can be done in like order of C and the volume of that cut. Yeah, and then this is known before in the previous. Yeah, but it's mostly use local algorithm to do the research. Yeah. So, yeah. Thanks for the question. So now I will give you only this idea about computing something called covering set. So let me define the covering set. So the definition is this: given a graph G, I want to find the a set of nodes V. It's called TC covering if it is a vertex space that contains some C cut that split T. But more formally, is this. So it's a set of vertices such that if there is a cut T that split the terminal into A and B, then that will contain that Z will contain that mean cut, mean AB cut. This is called cut covering set. And there are two steps that prove. The first is key lemma, say that given such a covering set, we can output this is a Sparsifier of size Z union T in linear time. So this is the first key lemma, and then the second is the key technical part is that we can compute this set deterministically almost linear time, and then we get the covering set of this size. And I just want to remark that this is a similar approach to the edge version in the afterwards. We also try to find the covering set, but for the edge version. But here we get for the vertex version. And then for the, I'm gonna tell you how to do how to prove the key lemma, like why it is enough to compute covering set to get a Sparsifier.
But covering set is like much stronger than what you need, right?
Exactly. Yeah. In fact, we only need to like cover
Just one cut.
just one. It's enough. Yeah. But yeah. So there's also a nice open question whether or not you can shape this to be policy instead of exponential. Maybe you don't need this notion of covering set. You might get something bigger, and maybe you get something better. Yeah, that's a great question. Okay. At least I'm gonna there's some nice idea how to turn the given covering set, how to turn into the graph into Sparsifier. So we're gonna use something called vertex contraction. Have you ever seen something like vertex contraction before? No, right? Okay, good. So it's an analog of edge contraction. How do you contract an edge? You just contract, merge them into one node, right? Yeah, but what does it mean for the vertex contraction? But we essentially need the following property that whatever it is, when we contract them, the cut inside the contracted graph must still be the cut in the original graph. So we want the smaller graph to kind of always have the larger mean, the mean cut in the smaller graph can only increase. Yeah, whatever that is. Now I'm gonna tell you what that is. Okay, but before that, let me motivate the motivation by this. So look at an edge contraction. So for example, the graph look like this. We can contract this edge, okay, into one node. And then what kind of property do we guarantee? It says that take the cut in the smaller graph. This cut corresponds to the cut in the original graph. Basically, because you take this cut and then you can uncontract them, and then you get the original graph. So there's no new cut. So we want this property. And how about vertex, right? So this is something that so here's a definition. So the definition is also due to the first work in the Sparsifier. The operation is the following: that if I want to contract V, then I add the clique among the neighbors and then remove the vertex. Okay? So it's in this example, the contraction operation will be this. Okay, this is called vertex contraction. And the key property that it's not difficult to see, but that a vertex cut in the smaller graph corresponds to the vertex cut in the original graph. But one at least quick intuition why this is the case is that in the contracted graph, we kind of add the clique here. And then any vertex separator, you cannot separate the clique, right? So the separator in this, the vertex cut here, it has to split the clique into one same side, right? Which means that if you take that cut and split the clique into the same side, when you undo the contraction, then that cut is still a valid cut in the original graph.
So the vertex main cut size might increase after the.
Yeah, it might increase, but it never decrease. Yes, that's the property that we need, and this is the vertex. The vertex analog of the vertex contraction. Yeah, the contraction analog, and there's also another name called the closure also, but I like this name better. Now, given this operation that we have this property, we can convert into Sparsifier very easily. So here's the algorithm. So I will only show you the existence. Okay. So the algorithm is this. Start with G. I contract everything else except T union set. T union the covering set. I do the vertex contraction or the, and then to show that the graph here is a Sparsifier, we need to show two things. One is like the graph is cut recoverable. And if there's some cut split T, then that graph has to preserve some cut, okay? And the first property that the graph S is cut recoverable is given by this property, right? Whenever we do the contraction, we never introduce a new cut. The mean cut can only increase. This happen, we can do inductively, and then it happened. And then to see the second property, let's consider the following cut. The second property is that if there's a cut C that split the terminal T into A and B, let's say A and B like this, then we need to show that the graph H must have some AB cut, it must preserve some AB cut. And consider such a cut. How do you expect that to happen? It's given by this fact that Z is a TC covering set. TC covering, it means that it contains this guy. And it means that when we do the vertex contraction outside Z, it will not touch this cut. And therefore, this cut has to also remain the valid cut in the smaller graph. Okay. I mean, that's conclude the undefined level of the Sparsifier and what we talk. Then the remaining outstanding open problems include can we get this ultimately in near linear time for any connectivity? So we make the progress by getting for constant connectivity. And even generally, can we break MN time deterministically is still a great question. And also there are some variant like directed version and a weighted version are also like quite open. We don't even know the linear time algorithm, even we use randomness. Yes. Yeah, for directed, the best known is like MC square and then N square both randomized. And then for weighted, we know only the high single round cable, like running time of MN randomized, and then kappa 0 means unweighted connectivity. And with that, I would like to conclude my talk.
Yes, I have one kind of technical question. So when you define like a vertex contraction,
Yeah.
then you contract bunch of vertices. So does the order matter or like it doesn't?
So it's not clear, yeah, but the order doesn't matter. It's so what one can show that if you
So you might get different graph, but then like your claims are just zero.
I think you get the same graph regardless of the
Oh,
order.
I see.
you will get a same graph.
And then it's like correct to say that I'm gonna like it's like everything outside of S union T, then they have like some neighbors. And
Just
then,
add
yeah.
a click of the
Oh,
you have a set.
neighbors.
So no, you need to, and if you can do something like this. So first, you take the connected component, and then the neighbor of that you can add all the click.
Oh, okay.
It has to be like connected component, and then you add the click. Yeah, and then you can show that if you do that on the connected component, it's the same thing. And then you can decompose into this connected component and do it separately. Yeah.
I think I missed this detail, but where does the 2 to the C runtime come from? What's the ingredient that?
It's actually high inside this one, this theorem. But
So if you could improve that theorem to faster runtime, would that remove your C dependence or?
yes,
improve it?
exactly. This is the only bottleneck, I think.
Do you think that should be improvable? Like, is that the place to look, or is?
It's a great question. Yeah, I never tried it. I have not tried it long enough. Yeah.
Sure.
Like this thing with small size exists. We just don't know how to compute it fast.
I see.
More questions?
Are there other interesting applications of the vertex contraction?
Oh, the vertex contraction. I have seen another like vertex Sparsifier in the same flow. I also say that they try to do something similar to Haskell, but I'm not sure. But I feel like it's a generic operation.
Let's thanks for watching again.